Hello and welcome all to this learning capsule on fluid mechanics for process engineers. I am Naren from the Chemical Engineering Department, School of Chemical and Biotechnology, SASTRA. I handle this course on CHE 105 Fluid Mechanics for Process Engineers for BTech Chemical Engineering and Biotechnology degree program at SASTRA. We are in learning capsule 25.1, wherein we are going to see about flow through pipe. Let's see about what is the learning outcome connected with this learning capsule. We will see how to make a shell balance on a control volume in a flow through pipe, and we use this shell balance on a flow through pipe to derive a differential equation for a flow through pipe. So what I mean by here is differential equation for a flow through pipe is the differential equation to describe the fluid flow through pipe. Now before we do the derivation, let's understand what is the flow that are we going to consider in this learning capsule. So in other words, is there any assumption that we want to consider for this particular concept? Now as shown in this schematic sketch, so let's consider this is a cylindrical cross section pipe, and the flow is in this direction from left to right. So you have a flow primarily occurring through this pipe. Now that's a very schematic sketch, and from this schematic sketch I am very sure you will be able to identify or list the assumption. The very first assumption is that we want to consider only horizontal flow through pipe. So that means we are not going to consider about inclined or vertical flows now, either upward or downward. We are only going to consider horizontal flows. The second is the system is considered to be at steady state. So that means there is no transient with respect to the flow. The third and the fourth are primarily the fluid assumptions. We assume the fluid to be of constant density fluid, and it is a Newtonian fluid. So this Newtonian fluid enables you to describe how shear stress can be related to the shear rate or the velocity gradient. So primarily these are the four assumptions that I require to start with. Now what is the approach that we are going to see when we are going to derive? So again I have redrawn the flow through pipe. So we are going to focus the approach of Eulerian approach. So that means we are going to have a fixed reference frame. So that means the observer is at rest at some point. Let's say the observer is at this point, and from this point he just sees what happens when the fluid flows through the pipe. And then we are going to consider a differential control volume, and it is in the differential control volume we are going to describe this flow feature. We are going to derive this equation. Now what could be this control volume? If you ask this, now like control volume can be like this. Control volume can be of this shape. So that means in essence control volume can be of any arbitrary infinitesimally small region of space that we want to focus and through which the flow is actually taking place. So this flow coming in and going out. So this is conceptually okay. This choice of control volume, so that means like this arbitrary choice of control volume makes mathematics difficult for us to handle, right? So it's not like it is conceptually incorrect. In principle we can have any differentially small region of space to be focused within the system, and that can be taken as a control volume as long as the continuum hypothesis is valid. But then if you take very arbitrary shape and try to describe the flow, the mathematics becomes difficult. So that means we want to necessarily take a control volume which helps us to do mathematics. Now it is with this perspective we want to take a regular control volume. What I mean by a regular control volume here is the geometry of the control volume. So control volume is what I write like this, CB. The geometry of the control volume is well defined so that we can do mathematics on this. Now, because this system is a cylindrical system, we end up taking a cylindrical control volume. So that means we take a very short cylinder like this. So we take a very short cylinder like this. So that means we are focusing this fictitious imaginary space. So this is a very fictitious imaginary space. So this is an imaginary space within the pipe that is point of our focus. So it is for this control volume we want to write the equations. So that means flow is now going through this control volume and coming out, and we want to describe what is happening in this control volume. So that means now we saw what is the flow assumptions, what is the assumption we make about the system. We then talked about the control volume, and now we have figured in the control volume. So the next point is obviously to write expressions for the control volume. Now before we write expressions for control volume, we just put certain notations as you see here in this slide so that it is easier for us to write. So this is an Eulerian approach. So that means we have a fixed reference frame. That's what I have described here. So the reference frame is not moving. I have taken a cylindrical control volume. So the two edges of the control volume I have written as Z and Z plus delta Z. So that means this control volume length is given as delta Z, and this is the diameter. So this is the radial coordinate of the control volume. So that means what you have here is primarily the axis. So this is the axis of the imaginary control volume that we have considered. Now comes to the point, what are we going to write? So we have now identified the domain on which we want to write the equation. But the next question, what are we going to write? We are going to write shell balance, right? And we are going to write, as we stated above, steady state shell balance. Now what do you mean by this shell balance is the steady state, or otherwise called as momentum balance. Or I can say that this is the force balance on the control volume. Now because this is the fluid flow is steady, there is no acceleration of fluid within this control volume. So if there is no acceleration of fluid as it passes through this control volume, so as it passes through this control volume, if there is no acceleration of the fluid flow, that means sum of all the forces acting on this control volume is 0. Now the question comes, what forces are we going to consider? Right, this is because this is a 0 vector because it is a steady state. So it's a steady state, so there is no acceleration that we have taken. But the question is now what forces? Now we need to account, so here we need to account the forces that are significant for flow through pipe. All forces that are significant in a flow through pipe context have to be accounted. The first force that comes to, can you just think of all these forces? The first force that probably comes to your mind is the gravity force, but because we have already seen it is an horizontal system, this is not accounted. The next force which causes the fluid flow to happen primarily is a force due to the pressure drop, or the pressure force, or which is the external force which is applied and which causes the fluid to move. And because the fluid layers are moving, and we have already said it's a Newtonian fluid, so that means the fluid has a finite viscosity and the fluids are moving. So between the layers of fluid, or between the fluid layers within this control volume, the momentum is transferred, which is given by the shear stress. So the other significant force that we are consider is a force due to the shear stress. So let me go to the next slide. So let me just add this control volume again. So we have a control volume like this, and what are we going to do is the force balance on this control volume. So what is this force balance is a sum of the significant forces, and the significant forces is pressure force and the shear stress on this control volume should be equal to 0. Now note here, this is an algebraic addition, so this is a signed summation. So depending upon the sign convention of the forces, you need to add these forces, and it is just not a scalar addition. Now let's come to the first quantity, which is the pressure force. Now what is the direction in which the pressure force is acting? So if you see here, pressure is compressive in nature, so this will be the pressure that is acting on this plane at Z, and this will be the pressure that is acting on the plane Z plus delta Z. Note, the blue arrows denote the flow, whereas the red arrows that I am marking now denotes the sign of the pressure acting on this fluid element. So as I described, the pressure is acting on this cross section that I am now shading in red. So similarly, it is acting on this cross section of this element. So that's the direction with respect to the pressure. What about the shear stress? Now shear stress is something which is acting on the lateral surface because of the fluid motion. So that means shear is acting in a direction opposite to the fluid flow. Now if I consider flow in only in one direction as shown here, so that means if the flow is only going from Z to Z plus delta Z and it is not crossing this fluid element, so that means if you see in the original pipe, what we mean here is if I have a control volume like this, we are saying that this is not happening. The fluid flow is not crossing the radial direction, it is only going through the axial direction. So this is the axial direction of flow. So this is the axial direction of flow because this is the Z direction. If the flow is only in the axial direction, if that is what we are going to consider now as another assumption here, so that means this is like a fictitious wall. So what you see here is a fictitious wall, and this wall, on this wall you have the shear stress acting because of the moving fluid layers. So now you have got the direction of force and the direction of the shear stress. So the direction of force due to the pressure is this, what is described here, and what is here in yellow is the direction of the force due to the shear stress. Now seeing this direction, it is very clear now for you to write this balance. So that means force due to the pressure at Z should be equal to the force due to the pressure at Z plus delta Z plus the force due to the shear stress in the region delta Z, because you can clearly see from the direction of arrows, these two are on one side of the equalities operator. So this is the equality operator, and this pressure force is on the other direction of equality operator. So that means the pressure on Z is counterbalanced by what is the pressure that is acting on this layer plus whatever is the opposing shear force that is acting on a fictitious wall. Remember, this is a fictitious wall of this control volume. Now what is the expression for pressure? The expression of pressure, the force due to the pressure force, is pressure times the cross sectional area on which it is acting, and the expression for shear stress is the force due to the shear stress is the shear stress time, and this is S is the surface area on which it is acting. So you have here pressure and times area at Z should be equal to pressure and area times Z plus delta Z plus tau times the surface area over the region delta Z. Now what is the cross sectional area? Now if you clearly see this part which is shaded in red, you know what is the cross sectional area for a cylindrical element. So for a cylindrical element, the cross section area is given by pi r square, and the surface area is this on the lateral surface area. So the lateral surface area wherein the shear stress acts is given by 2 pi r into the spacing of the cylindrical element delta z. So let's substitute here. So that means P times pi r square at z equal to P times pi r square both evaluated at z plus delta z plus tau times 2 pi r into delta z, and this is what we get. Now what are we going to do is we are going to divide by the volume of the control volume that you have taken. What is the volume of this control volume? That is given by uh, pi r square times delta z. That's primarily the volume. Now why are we doing this step, right? Can you just think, why are we doing this step? Why need to divide this equation? Now that's for a very simple reason that I would explain in this diagram. It's not only for this control volume that our equation should be valid. Even if we take a small control volume like this, even if we take a control volume of here, or we take control volume of this, or a very small control volume, no matter what is the actual size of the control volume, we want this equation to be valid. And that's what we mean by we divide the control volume, and we are like fictitiously making this control volume shrink to zero. So this is what we are shrinking the volume of the control volume to zero, and we represent this mathematically as limit delta v of that variable goes to zero, and that's what we are going to do. If we do that, so if we divide by the volume of this control volume element and take this term, so what you see as this term on this side, and rearrange, you end up with a differential equation which is dp by dz plus 2 tau by r equal to 0, right? And this involves obviously the assumption based of this control volume that is drawn, that the value of r at z and the value of r at z plus delta z is essentially the same, because now you are shrinking it. So when you are shrinking it, this radius does not really matters, and it becomes constant. So which is implicit in this step. So you are dividing by this volume and then taking the limits as delta v, the control volume goes to 0, which means the limit delta z goes to 0 and r goes to 0. So you are really making it short. You end up in this governing equation. So that's the summary of this learning capsule. So we considered about a flow through pipe. Now what is the assumption under which we considered? We said it is horizontal, steady, constant density, and Newtonian fluid. We didn't yet make use of this. We have actually made use of horizontal, steady, and constant density assumption, so on, but we will eventually make this use of this Newtonian assumption also in the subsequent learning capsule. You will see that. So it is this we considered, and we considered the forces. What are the two significant forces that we considered? One is the pressure force and the force due to the shear stress. And when we balance this under steady state condition, we end up in a differential equation dp by dz plus 2 tau by r equal to 0. So this is the governing equation that describes the flow in a horizontal steady flow of a constant density Newtonian fluid through a small differential element. Now what about this is a differential equation and then we need to solve it? Can you think of means of solving this? That's what I want you to do it. I'll also suggest some readings for this learning capsule. You can go through this reading and then do it. Let's see the suggested reading. The suggested readings are there in the slide. So I would wish you to go through the chapter 5 of McCabe and Smith Harriot 7th edition of Unit Operations in Chemical Engineering. With this, I end this learning capsule, and thanks for watching this video. See you, bye.